Okay, proof set theory and logic. What's up, everybody? So everyone's looking at their exams, which we just passed back. Hopefully it went great. If it didn't go great, don't worry. It's just one test. There's many tests, right? You have plenty of chances to redeem yourself. No one did so badly they can't. The distribution for the grades, I would say, was pretty much like a nice, kind of fell off pretty quickly. Or maybe I should draw this like a little bit more like it was like it was almost like a bell curve, right? A standard old normal distribution, but it was weighted like a little bit more towards the front. So kind of like that, right? So it was like about the same number as A's as F's, but C's were certainly the most common, and then D's and B's, the B's were a little bit higher than the D's. So that's pretty much how it went. Which, about what, in the vicinity of what I expect. Sometimes it leans a little bit more heavily towards the B's than the C's, but overall, pretty good. Right on. I would say by far and away the most common error on the whole exam was the one about proving the product of two odds is odd. Almost everybody seemed to prove instead that the square of an odd number is odd. There were only a couple people who didn't do this, so if you didn't, good job. If you did do it, okay, it's an easy mistake to make, but be careful. That is, make sure that, like when you're doing something like, for instance, saying like, oh, okay, well, if n is an odd integer, then it's of the form 2k plus 1 for some integer k. And if m is an odd integer, well, then it must be of the same form. Yes, but it need not be the same value of k, if that makes sense. If you use the same value of k, then what you are saying is that m and n are equal, right? So that's the distinction right there. That is, you correctly identified the form, but much of the detail of the proof was effectively lost, right? You instead proved a far more restrictive statement, right? There's certainly a subcase of the other one, but it's not quite the same. On the proving that an argument is valid part, which was a large portion of it, answers varied pretty substantially, and that's totally fine. You can have totally different verifications of the validity of an argument. You can reach the same place in multiple different ways. So I tried to grade it based on your the clarity of your intention to some extent. That is, if you made like one leap that wasn't totally well justified, but seemed like, I was like, okay, it's like reasonable, like, oh, that's like a common misunderstanding, and you got to where you wanted to, and you like showed me an argument that had like one flaw in it, right? I tried to be pretty lenient on that, but if you made like lots and lots of leaps to get to the place you wanted to go, I was, like the number of incorrect steps, I tried to scale the grade essentially in proportion to that. And then if you didn't end up getting to where you wanted to go and you also made lots of incorrect steps, then perhaps you didn't score too well in some of those ones, which did happen a few times where people would, make up an incorrect step and then, get there or get to somewhere else other than where you wanted to go. So be careful to make sure that your final step is indeed the thing you wanted to show. One thing I did see a couple of times, and I don't mean to call anyone out in particular on this, but because it happened more than once, I really want to make sure that we actually hammer this one home, because otherwise it will throw people off later in the class with your lines of reasoning that you'll employ. An argument I seem to see a fair bit would people would have some sort of like, you'd have some, like steps like 1, 2, 3, and then at some point you would have like a step where you'd have some statement. Say for instance, like you had like P or Q, and then in the next line people would say not P or Q, and then their justification was they would say negation on 4. And I want to say that this is not a correct rule of inference. That is the argument P, therefore not P. No, right? What this would be saying like P is true, therefore not P is true. That is never going to happen, right? You can never have a thing and not the thing simultaneously be true. Does that make sense? It's one or the other. So just because you can negate something does not mean that negation is itself a valid rule of inference, right? I saw a few things like this where people would just perform some sort of an operation on of something that you had in some line, and claim that you got things from that. Like I also saw people go like, oh, here I have, say, for instance, like P, and then I would say, I would see someone say like, so P implies Q, and write implication. And you're right that in the sense that this is an implication involving 4, right? But it is not the case that if you have, this is not true. P, therefore P implies Q. You should think carefully about that, right? So there's a few cases like this where people would reference like some sort of an operation that you could perform on a proposition of some type, and then try to use this to just change it into the thing you wanted. I understand that that's like an appealing idea, that you could just take something and then just do stuff to it, and then it is the thing you want. Of course, that's nice, but the idea is to do so in a way that preserves the truth structure of your argument. And just negating things at will flips the truth structure, right? It takes a true thing and turns it into a false thing. And so you got to be a little careful with things like that. There's also a number of places where people kind of were pretty hand-wavy on some stuff. I get it. I get the appeal to do that. Every person wants to do that. And honestly, like the further along you go in mathematics, the more people like to wave their hands about stuff. And by hand-waving, what I mean is that like you made a correct leap in logic, and your justification for it like suggested what the actual argument was, but you did not actually go about making the argument, right? You went like, and so by standard algebra, there you go, right? And it's like, okay, you can kind of wave your hands. It's like, well, you know how it goes, right? And hand waving is fine to some extent, but especially if you're trying at this point in the class to very clearly show a proof, you should minimize the amount of hand waving you do. There can be like a little bit of hand waving, a few skip steps. It's not like you need to write out, k squared as k times k or something like that. You can perform basic algebra steps. You can combine a couple things in one step. That's fine. But if it's kind of like the core of your argument, you shouldn't hand wave it away, right? Like for instance, in the induction proof, there was a number of times where I would see people go like, oh, okay, so you've got like the sum from I equals 1 to k plus 1 of I cubed, and you went, okay, well, this is the sum from I equals 1 to k of I cubed plus k plus 1 cubed, and I was like, okay, this is great. And then you went like, okay, well, I forget what it's supposed to be equal to. Is it k times k plus 1 squared or something like that?
K squared times k plus 1 squared over 4.
Thanks. People would write this, and then they would go, okay. And then I saw some of these where people would go, ... equals. And it's like, yeah, okay, I get it. Like that is the structure of the argument. But the part where you turn this into this is kind of the core of the argument, right? Just doing a ... like, that if you are like a professional mathematician and like you're writing to an audience of people who have done like thousands of induction proofs and like know exactly how it goes, this is perhaps appropriate, right? But if the point of the problem is to show that you know how to do an induction proof, I would recommend showing the actual induction step, right? That would be kind of what I'm looking for in the answer, right? To see that you're able to perform that part. So I would encourage you to not skip the steps, especially if the steps are incredibly crucial to your argument. Anyways, that's a lot of stuff to go over there, but cool. If you have questions on your grade, if you believe that I marked something unfairly or I graded something too harshly, there is some possibility of that. I certainly don't want to discount that. It is true. that when you grade many, many exams, and especially when almost all of the answers are different, right? Almost everyone used different approaches to different problems, to the same problem even in many cases. It can be occasionally challenging to come up with like a standardized and fair rubric, especially when you have as many different types of answers as there are people in the class. So if you think I was too harsh on one of them, come talk to me. We can look over it and we can figure it out. I don't think I did that too much. But if you think so, please come discuss it. Don't just, stomp your feet and write me a bad review. Let me know, right? Not that I will give you free points in return for a good review, but if you think you have a legitimate case, please let me know. I am always open to hearing legitimate cases. Cool. So how's everyone feeling? Bad? Good? Suitably humbled? Maybe, I don't know. Mathematics is always a humbling thing, right? It is this, I don't know. For most people, it feels like some sort of like a yardstick to measure your shortcomings against, but I hope you don't see it that way and instead see it as a puzzle to be solved, right? Some new untraveled land to explore. And if you got a bad score, it just means you haven't seen it all yet. So keep going. You'll get there. It'll happen. It's all good. It's just one exam. So let's get back into talking about relations. Recall. Oh, throw my pet against the wall. So recall a relation from A to B is a subset of A cross B. Notation. Notation. What we wrote for relations is we said, I'll say it this way, let R contained in A cross A be a relation on A. Often, we denote AB in R by some sort of a symbol between A and B. That is, instead of writing that ordered pairs belong to the relation, in the same way we write 1/2 equals 2/4, right? We will instead write a symbol between the two things instead of just writing the ordered pair. But this is just a shorthand for saying that the ordered pair belongs to the relation. Cool? Okay. We saw a few examples of this last time. So we had some examples. We had, for instance, less than or equal to, less than, greater than or equal to, greater than, the equal sign. This is an example of a relation. All of these things define relations in the usual way on whatever set you happen to be using them on. Okay, cool. You can make up other ones. We did other wild ones. For instance, you could relate people to hair colors. We did that one. Okay, so there's many different types of relations, as varied as you can imagine. All they are is subsets of ordered pairs. Okay, easy enough. Basically, the idea of relations is just, hey, you want to say something about two things. Well, you just have to decide which pairs of things you can say that about, and then you've described the thing in some sense. Is that clear? That is, A cross A, the whole thing, this is just all possible pairs of things in A. If you want to say some stuff about which things in A are somehow like other things in A, all you have to do is select a subset of that where your condition that you want to express is satisfied. So you could define this condition, for instance, with a predicate. It's a reasonable thing to do. And then you could build your relation via comprehension, something like that. Totally reasonable. Also, other ways to do it, you could just by fiat declare it to be a certain way, right? You could just make up any old subset you want. Totally fine. All of them relations. All right. Now, if you also recall, we had some nice properties for relations. So I will highlight a couple of them really quickly, just so you remember. Let A be a non-empty set and sim, this tilde, a relation on A. Then we say sim is, this tilde is, 1, reflexive if A is related to A for all A in A. 2, symmetric if A is related to B implies B is related to A for all A and B in A. Notice this doesn't mean that A is related to B for all A and B in A, but that if A is related to B, then B is related to A. Okay, we had antisymmetric if A is related to B and B is related to A implies that A is equal to B for all A and B in A, and transitive, 4, got to write my 4 first, 4, and transitive if A is related to B and B is related to C implies A is related to C for all A, B, and C in A. Okay, so we had a couple different properties. There were a few more, there's many more that we could list. There's a few more that we didn't list but briefly talked about. For instance, antisymmetric is not the opposite of symmetric. The opposite of symmetric would be asymmetric. Asymmetric would say if A is related to B implies that B is not related to A. This would be something like, for instance, the less than sign would be asymmetric. Okay, cool. There are plenty of other ones you can make up. There's a whole laundry list of potential types you can come up with. You could even make up your own type, just come up with some esoteric property and name it, whatever you want. Okay, cool. But these are ones that are particularly important. Now today we're going to focus in on a chunk of these that play an extremely key role in mathematics. So quickly, a definition. I've gone back a page. So a quick definition. Let A be a set, or I'll even be clear, a non-empty. And let tilde, sim, be a relation on A. If tilde is reflexive, symmetric, and transitive, we say that relation is an equivalence relation. So just think about your good old-fashioned equal sign. Reflexive, symmetric, and transitive. If I go back to this other board quickly to draw on it, let's think about it. So is a number equal to itself, or any number? You've got reflexivity. If a number is equal to another number, does that imply the second number is equal to the first? Yeah, absolutely. We've got symmetry. Okay. Now, anti-symmetry, I guess you kind of intrinsically have something like that. If you have a number is equal to another number, and the second number is equal to the first number, that certainly does imply that the two numbers are in fact equal, right? Okay, fine. But transitivity is also definitely the case, right? Okay, so transitivity, this comes out for nice. This is an important one in the sense that if 1/2 is equal to 2/4 and 2/4 is equal to 8/16, we all know that that means that 1/2 is equal to 8/16, right? Okay, cool. This is like how you tend to, in practice, go about, taking a fraction and turning it into lowest terms, right? You cancel terms and you keep going and you keep going until you get to the bottom, right? So that process that allows you to keep going, the reason we can do the whole business where we're writing like a proof and we go like this thing is equal to this thing is equal to this thing is equal to this thing, this is just transitivity in action, right? This thing is equal to that, and that thing is equal to this, and that thing is equal to this, so this thing is equal to that. This notation even suggests it. So transitivity, highly important. Okay, cool. So we've definitely got transitivity. Anti-symmetry is a more interesting one since we are using some kind of a equal sign right there already. We'll talk about that more later. But for now, let's jump back over to equivalence relations and let's start talking about what you can do with them. Probably the nicest thing you can do with them is define what's called equivalence classes. That is, we're able to take, with an equivalence relation, a large set of things and kind of collapse it down into a much nicer, smaller set of things. In the same way that you don't treat 1/2 and 2/4 as if they are different numbers, but instead just different representatives of the same element, an equivalence relation allows us to take a large chunk of things and identify many of them together in a cohesive, nice way. Okay, so here is the definition. Let A be a non-empty set and let tilde, sim here, be an equivalence relation on A. For each little a and big A, define the set bracket A, which we will say is equal to the set of B's in A, such that A is related to B, and call it the equivalence class of that little a. Okay, so you might look at an equivalence class and you might say to yourself, why can't I just do this for any relation? And the answer is that you can. You could do it for any old relation you want. But you will not enjoy the same nice properties as you get with an equivalence relation. We'll talk about some of them briefly, but just think about it quickly. If, for instance, you don't have, say, symmetry, then saying, oh, B belongs to the equivalence class of A does not necessarily mean that A belongs to the equivalence class of B, right? So if you don't have symmetry, these guys will not work quite as well in that regard, for sure. All right, that would be like having something where like, oh, 1/2 is equal to 2/4 doesn't mean that 2/4 is equal to 1/2, right? You could imagine that you could come up with some sort of a thing where you have nice situations, or you have situations where something like that would be useful, but you won't get the same nice kind of properties that you have, that you enjoy with things like fractions, where you're able to pick any representative from the class to use as a stand-in for any other one, right? That is, you can replace 1/2 with 2/4, with 100 200ths at will, right? They all work exactly the same. Having one in the equivalence class of the other implies the other is in the equivalence class of the first, and you're able to switch between them at will. Now, this is what makes the equivalence part of the relation important. You want, for instance, reflexivity to know that A belongs to its own equivalence class. Without reflexivity, you wouldn't have necessarily an element in its own equivalence class, which seems kind of weird, right? Okay. Similarly, the same business with the symmetry that we talked about, but transitivity is perhaps the most important one because we use transitivity, as I pointed out before, all of the time when we're doing a series of manipulations. Without transitivity, anytime we do a series of manipulations, you have to justify each step. And it is possible without transitivity to have some, to perform a series of manipulations and get something that is not equal to what you started with. So we must be careful and make sure that our relation is actually an equivalence relation. Otherwise, we will not enjoy all of the nice properties that we would like to have. So what kind of properties am I talking about? Well, let's look at some of them. Theorem. Here's a nice one. Let A be a non-empty set, and let tilde be an equivalence relation on A. Then we have the following two items. One, for each A in A belongs to its own equivalence class. That is, the equivalence classes are not empty. Okay. And two, if the equivalence class belonging to A is not equal to the equivalence class belonging to B, then the equivalence class belonging to A intersect the equivalence class belonging to B is equal to the empty set. This is perhaps the most important one. That is, equivalence classes partition the set. Here's a way of thinking about it. You've got a big old set A, and when you impose an equivalence relation, what you're doing is you're saying, okay, here's A, like a thing. Here's all of the stuff that is similar to it. Here's another thing. Here's all of the stuff that is similar to it. And there is no overlap between B and A's equivalence class unless they are the same. That is, if they are not identically the same thing, they are totally disjoint. Does that make sense? Basically, equivalence relations let you take a set and cut it into pieces. Yeah? Here is an example of an equivalence relation that you have all seen before. It looks like this picture. Suppose you have a pizza. Have you ever taken a pizza and gone slice, 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 slice? When you did that, you partitioned your pizza into chunks. Yeah? You assigned each point on the pizza to a slice. The slices are the equivalence classes, right? You're saying, well, this piece of the pizza right here versus this piece belong to the same slice. Does that make sense? Okay, so here's an example of an equivalence relation. Cutting pizza. You can imagine many other things like this. For instance, Halloween, you're trick-or-treating, right? You got some kids coming up. You're giving out your candy. You're assigning an equivalence relation to your candy. The equivalence classes are the children that you give each bit to, right? Maybe you give a few pieces to each kid, right? More than one thing in each equivalence class, yeah? But you don't give one piece of candy to two kids unless you're really stingy, right? And that's what makes it an equivalence relation. That is, no overlap. Okay, cool. So let's go through and prove this. Proof. All right. For part 1, recall that an equivalence relation is reflexive by definition. So A is related to A for all A in big A. That is, A is in the equivalence class of A, which, if you recall, is the set of elements B in A such that A is related to B. So if A is related to itself, there's a terrible A right there, then it certainly belongs to the class of all things that are related to A. Yeah? Do you agree with that? Just from reflexivity? Reflexivity says, hey, you got a thing, it's related to itself. If the equivalence class is the collection of all things that are related to something, then certainly you have that something in its own equivalence class. Nice. For part 2, we'll have to do something a little bit more fun. Any questions about part 1 before we jump to part 2? Oh, the day when you pass back a test is always an interesting day because the mood in the room drops so much. I'm sorry, guys. Okay, let's do part 2. For part 2, we prove the equivalent statement, which says that if the equivalence class of A intersect the equivalence class of B is not equal to the empty set, then A is equal to B. A's equivalence class is equal to B's equivalence class, i.e., we prove the contrapositive. Make sense? So if the intersection of two equivalence classes is non-empty, then the equivalence classes are the same. That's what we'll prove, which is equivalent to the equivalence classes are not the same, implies their intersection is empty. That is, instead of proving P implies Q, we will prove not Q implies not P, which is the same, that has the same truth values. It's a logically equivalent statement. Cool? All right, let's do it. How would you start? Does anyone have a good idea of how to start?
Suppose a equivalence class of A intersect equivalence class of B not equal to the empty set.
Okay, yeah, that's a great place to start. Okay, so suppose the equivalence class of A intersect the equivalence class of B is not equal to the empty set. Then let's say X belong to that intersection. After all, we've just assumed that there is something in that intersection. Yeah? Okay. So here's what we'll do. Let's take something belonging to the equivalence class of A, and let's show that it belongs to the equivalence class of B. Then, so if X is in A intersect B, would you agree that A is similar to X and B is similar to X? Yeah? It's a reasonable statement, right? That's what it means to belong to each equivalence class. So if it lives in the intersection, then it satisfies both. Yeah?
Question.
Yes.
Since B is symmetric, can we say like X makes a relation with B?
Oh, okay.
So then you
So by symmetry, you're saying
right?
X is related to B.
Yeah. By transitivity, A is related to B. Would that like B?
Okay, yeah, so you've just shown that A is related to B. Okay, nice. This works. This is pretty good. So if you want to go about showing that they are the same, let's use this fact. We've just shown that A and B are related by symmetry and transitivity. A nice clean approach right there. I like it. Okay. So how can we use this to show that the equivalence classes are the same? Well, I know a great way to show that two sets are the same. Let's show that one is contained in the other and the other is contained in the first. So here, I will erase this so we can keep it on the same board. Stupid little thing. Proof continued. We use this fact to show A is the equivalence class of A is contained in the equivalence class of B, and to show the equivalence class of B is contained within the equivalence class of A, allowing us to conclude the equivalence class of A is equal to the equivalence class of B, which, remember, is the thing that we wanted to show. Yeah? Okay, wow, some noisy stuff going on out there, huh? Yeah? All right, so to do this, let Y be in the equivalence class of A. Then Y is related to A, and since A is related to B, transitivity yields that Y is related to B. Thus, Y is in the equivalence class of B, right? So we started with an arbitrary element of the equivalence class of A, and we said, hey, to be in the equivalence class of A, this means you must be related to A. And since we know that A is related to B, transitivity says that we get that arbitrary element is related to B, or put it another way, it belongs to the equivalence class of B. So the equivalence class of A is contained in the equivalence class of B. Now, let's let Z be in the equivalence class of B. Then, Z is certainly related to B. Perhaps I am actually skipping a step right here in both of these. That is to say Y is related to A. What I really should say is I should say A is related to Y, and say, so by reflexivity, Y is related to A. If you want the full detail, right? Since after all, the way we defined an equivalence class, oh, I've written it over here, it is the set of all things such that A is related to that thing. That's the equivalence class of A. So if Y is in the equivalence class of A, then what we really have is that A is related to Y, and by symmetry, Y is related to A. So if we want to be fully technically correct, I should say that. If you'll permit me the skipped step here of not doing that and saying, hey, Z is related to B by symmetry, and since B is related to A by symmetry, that is, we have A is related to B, so B is related to A from symmetry. Z is related to A by transitivity. So Z belongs to the equivalence class of A, since the equivalence class of A consists of all things which A is related to. I guess I should even say further, Z is related to A by transitivity, and A is related to Z by symmetry. So Z is in the equivalence class of A, and we can conclude since we started with an arbitrary element of the equivalence class of B and showed that it belongs to the equivalence class of A, the equivalence class of B is indeed contained in the equivalence class of A. Therefore, the equivalence class of A is indeed equal to the equivalence class of B as desired. You can see how easy it is to want to skip some small steps right here and to use our natural intuition for how the equal sign works, which is like, like, oh, flip it, doesn't matter, right? But if we want to be fully rigorously careful, we should justify all of these steps. Of course, as you get used to working with these things, it is perfectly reasonable to intrinsically use symmetry without referencing it just because you have an equivalence relation. But I guess while we're proving some of these foundational properties, it is appropriate to make note of it every time we use it. All right, cool. Notice we're using transitivity, reflexivity, symmetry all over the place, right? Happening every which way. Okay. Notice part 1. In part 1, we say, hey, there's something in an equivalence class for each equivalence class, namely the thing that belongs to it, that generates it, the thing we use to denote it, yeah? A is in its own equivalence class. Okay, so the equivalence classes are not empty. That's good, because if they were empty, then when we go to the contrapositive here, this equivalence statement, which says that suppose the intersection of these equivalence classes is non-empty, then the equivalence classes are equal. If, for instance, one of these was the empty set, then this first condition could never be true, right? Oh, okay. So indeed, we have, from the first part, shown that this is at least possible to have that happen, right? And whenever it does happen, a non-empty intersection implies that they are exactly equal. So two equivalence classes are either totally disjoint, no overlap at all, or they are exactly the same thing. Kind of nice, right? No Venn diagrams. The circles are either the same circle or they are totally separate. Cool. It means you're cutting it into pieces. Okay, so cutting a set into pieces turns out to be a shockingly useful thing. That is, we do this all of the time. Here is an example of cutting a set into two pieces that you are all familiar with. Evens and odds, right? Evens and odds, well, that splits up the integers, the naturals, either one, both of them, into two chunks. One chunk of evens, one chunk of odds. You could represent these by equivalence classes, right? And hey, wouldn't you know it, you can perform arithmetic in a nice way and do so just by using a convenient representative element of each class. What's a convenient odd number? Maybe a small one. What about 1? What's a convenient even number? Maybe a small one. 2 small, what's even smaller? 0. How about that? Okay, if you're just doing it all with zeros and ones with representative elements from an equivalence class, does that sound like, something from the modern world? Yeah, it's how like computers talk to each other, right? They use equivalence classes. Nice. Okay, so let's look at another example. Here's another example. Okay, consider the equivalence relation I'll write it with 3 bars and a 5, congruent to 5, we'll call it, on Z, or congruent mod 5, perhaps you may call it, defined by A is triple bar equal subscript 5B if there exists an integer n so that b minus a is equal to 5n. There are 5 equivalence classes associated to, that's the worst D I've ever written, to to this relation, they are the following. The equivalence class of 0, which is equal to, I'll write it like this. Well, I've got 0. Okay, cool. What number would go so that number minus 0 is equal to 5 times n? What if n was, say, like 1? 5. What if n was negative 1? Negative 5. So you've got 0, I've got 5, I've got negative 5. What if n is 2? 10, negative 10, and so on, and so on. Okay, what's the equivalence class associated to 1? Does anyone have a sense that this will work somewhat similarly? Okay, something minus 1 is equal to 5 times n. What if n is equal to 1? You could use 6. 6 minus 1 is equal to 5 times 1. Yeah? Okay, 6. What if you use negative 6? That'd be fine. Negative 6 minus 1, or minus, yeah, okay, yeah, same business. So it's exactly the same. I'm just repeating myself now, and I'm going to get tongue-tied saying the exact same things again. But you just keep going, right? So negative 6, and now, oh, maybe wait a second, I've done something wrong here. I've written 6, not negative 6. I've said it now. Okay, so what minus 1 is equal to negative 5? Minus, what minus 1 is equal to? X minus 1 equals negative 5. X is equal to negative 4. Okay, good. I've written the wrong thing right there for the first time. Thank you. Okay, cool. So 6, cool. Now let's do another one. Okay, sweet. Great. Now let's do, instead of 5, let's do 10. 5 times 2. Yeah? All right. So what minus 1 is equal to 10? 11. And so on. Just one more than the previous. One more than the previous. Right? Shift it over by 1. Can you see the pattern? Shift it up by 1. Get minus 8, minus 3, 2, 7, 12, 3, and finally 4. Writing these, unfortunately, low on the board, but luckily we have picked up the pattern by this point, so it's not too terrible. All we're doing is we're taking each thing and we're going up by 1. Minus 7, minus 6, minus 2, minus 1, 3, 4, 8, 9, 13, 14. Cool. And once we get back to 5, wait a second. The equivalence class of 5, here's 5. Yeah? So the equivalence class of 5 falls into this one. The equivalence class of 6, equivalence class of 7, equivalence class of 8, equivalence class of 9. Okay, and then once again we get back to 10. Hey, equivalence class of 10. 10 belongs to it, right? Boom. And 11. Since we have 11 right there, then 12. And you can see how it just keeps going and going. Likewise, you can go in the opposite direction, right? You can count down. Minus 1, minus 2, minus 3, minus 4, minus 5, right? It splits everything up into multiples of 5, 1 more than a multiple of 5, 2 more than a multiple of 5, 3 more than a multiple of 5, 4 more than a multiple of 5. But once you get to 5 more than a multiple of 5, you are a multiple of 5, right? Oh, okay, cool. So this is, you know how there's even and odd divisible by 2 or not? This is like being, instead of even, it's like 5n, right? You're describing the different ways that things can be either divisible by 5 or not divisible by 5. There's one way to be divisible by 5 and 4 ways to not be divisible by 5. Cool. Kind of nice. All right. we'll talk more about equivalence classes next time, and we'll use them to construct the rational numbers, which is really fun. So, all right. I'll see you around next time. Have a good one. If anyone came in late and didn't get their exam, come grab it. I've got exams. What's your name again? Sorry, man.
Quinton Connolly.
There you go.
Good, thank you.
Sweet. Okay, yeah, let's look at this.
Yeah, I mean, I was just wondering because
No, let's check it out. Okay.
I just drew the truth
Because,
table
I mean,
because-
like, the entire kind of point was to avoid it, but it is small enough that I guess it is legit. You know what? I'll give you back some points on it.
okay.
Yeah, why not? Yeah. It is, I guess. You have a point. It is.
Well,
It does verify that it is a valid argument.
For sure.
I
And
didn't say,
I
you know,
convinced the office officer
yeah.
at one time and
No, you're
everything,
right.
yes.
That's true.
But
Yeah.
I totally get it though. I couldn't.
I should in future ones say, show the following argument is valid using the rules of inference.
For sure.
But I did not actually say that. So I'll give you full points. I'll give you 4 back on that. That's
Thank you.
fine.
I appreciate it.
I do remember saying that to you in office hours now. So
I didn't mean
16,
to point that out, but I just.
Hey, it's all good. You should point out stuff when you think you got a good point. And I do remember you saying that. So here's 16, and then that'll bump that up by 4 to 67.
Awesome.
All right. Yeah, it's all good. All right, cool.
Do you
I'll put
want
that in there.
Okay.
Yeah, I got Blackboard open right now.
Oh, perfect.
So
Sounds
easy.
great.
Yeah.
Well, thank you so much. I appreciate it.
Oh yeah, for sure. You got a good case there. That's fine.